In this video, to wrap up what we've been doing with electromagnetism, we're going to look at power transmission and how we get electricity around the country in the national grid. So everything gets started in the generating station. Let's look at the key. We've got everything, the red over in the left here is the generation. Then we've got the transmission in blue, the electricity getting passed around the country. We've got the distribution in green, and then it's going to get to the customer. So as I said, the first thing obviously is this generating station. And then what we learned about is this step up transformer that's going to increase the voltage up to, well, look, large values, 765, 500 kilovolts we're dealing with here, not just volts, kilovolts. That can be quite dangerous, which is why it's up on those wires that are high above the ground. Then we're going to get to the step down transformer, and then that's going to get to the customer. So 120 volts, 240 volts, that could be your home. And this is what we do. We step the voltage up to transmit it over large distances, and then we step it down again to make it safer and so that we can use it in the home. The question now really is, why do we bother? Well, we do it to save energy, to reduce losses. Now, if we look at this equation down here, P equals IV equals I squared R. So P equals IV should be very familiar to you, and P equals I squared R is just an extension from that, because if we take P equals IV and we know that V equals IR, then that's going to give us P equals I times R equals I squared R. Why do we bother with this? Well, it's purely for the fact that P equals I squared R is a much better equation to use most of the time, because you're going to get it wrong otherwise. If you really want to know why, at the end of the video I'll go into that in more detail, but really you don't need to bother. You just need to know that equation P equals I squared R, and what that means is that if we are transmitting our electricity over long distances along here, well, we're going to control our power losses. Okay, I'm going to keep saying power losses. What I'm talking about here are the resistance heating that we're going to get in the wire. And all that resistance heating is going to heat up the world around us, and it's not at all useful. So P equals I squared R, we have two things to control, therefore. We've got the current and we've got the resistance. Resistance, we can control that by using things like the area. We can use the length, and we can use the material. So obviously the length, make it as short as possible, but if you're going from town to town, then you can't control that too much. The area, we want a large area to have low resistance, but then it's going to cost more and it's going to be more difficult to hang up in the air. And the material, we're going to choose the best material, but really we're a bit limited. We choose the best things we can all there for that already, and then we're done. So what we need to focus on now is the current. If we can get the current to be as low as possible, then we're going to get the lowest power loss as well. So we want current to be low, because that then means that the power that we're losing is going to be low as well. So what I've covered in this lesson video is the national grid, which is how we transport the electricity around the country, step up transformers, high voltage, and then step down transformers. And I've also covered why we want to have the current to be as low as possible, because we want to have the power losses to be as low as possible. If you're still here, it's probably because you want to find out why we need to use that equation. As I said, you don't need to look into it. Okay, but let's just go over it for those of you who are interested. We've got a circuit over there. We think about the power supply being maybe 240 volts in the supply there. I've got 10 ohms, and so we can work out, if we want to, what the power is going to be dissipated by that resistor. Okay, that's fine. But what we've got to consider with this kind of a circuit is that the resistor is actually the wire. So here I've got a transmission where I'm going from 240 volts is my power supply over on the left there, and I'm going to supply power over onto the right, but it's going through a cable which has got a resistor, so I'm going to lose some power. Now what people tend to think is, right, let's try and work out what our voltage is going to be across there to work out what our power is going to be. Let's say we've got a 10 ohm resistor. I've got 240 volts, I've got 10 ohms, therefore my current is going to be I equals V over R is going to be equal to 240 over 10 equals 24 amps. And from that, we can then work out that P equals I squared R, or P equals IV, and work out that we're going to have 24 amps times 240 volts, 5,760 watts. And that is going to be completely wrong. Okay, so don't do that, because this is not really working out the power in this particular resistor. And the reason it's not working that out is that we don't actually have 240 volts across that resistor. We've got 240 volts over here. If we had 240 volts in that resistor there, let me put that in. If that was 240 volts there, then as the electricity came along, it's got a potential 240 volts, and then a potential difference of 240 volts there is going to mean that we ended up on this side with 0 volts. That's no use to anyone. So clearly that's not what is happening here. So let me get rid of that, and let's look at the correct way to do it. Now I'm still going to want to have my resistor. Okay, so we're still treating this as being a resistance wire. We're going to lose some over there, but we're going to decide in this particular circuit we've got a current is going to be equal to 1 amp. Okay, and the reason I'm doing that is I can then think, okay, so power equals 240 volts times 1 amp is going to be equal to 240 watts. I've got a certain amount of power that I'm producing in my generating station. I've put my power at 240 volts, so therefore its current is going to be 1 amp. Now let's have a look. We're going to put a voltmeter across this resistor. The resistor, let's keep that again at 10 ohms, and so we've got V equals IR equals 1 times 10 equals 10 volts. And if our electricity is flowing from this side, 240 volts, and then potential difference of 10 volts, that means that once it reaches the other side, we're going to be down to 230 volts. That's the power that we're losing. Okay, we're not losing everything. We've still got 230 volts on the other side to do some things, but we can now treat what we've got in the middle here as being our lost power. P equals I squared R is going to be the lost power. P equals I squared R equals 1 times 1, well, so 1 squared times 10 equals 10 watts. That's what we're losing. Now, if we're careful, if we do this correctly, I could use P equals IV, as long as I'm using my 10 volts up there. So I've got 1 times 10 equals 10 watts. The equation works as long as we use the correct voltage, 10 volts. But it's much, much simpler to use I squared R. Now, let's complete this by looking at the other circuit. Okay, so we've got 1000 volts over on this side. I still want to have my 10 ohm resistor in here. And I'm going to have a current flowing, but it's not going to be the 1 amps, because remember, we've got power equals 240 watts. That was what we were producing. This time that's going to be equal to I times V. It's just going to be equal to, V is 1,000, I times 1,000. Therefore, the current is going to be equal to 0.24 amps. Got a much lower current going through that wire now. Let's do what we did before. Check the voltage going across there, and V equals IR. So 0.24 times 10, so it's going to be 2.4 volts. So as the current, or as the electricity is flowing along here, it starts off at 1,000 volts. Then we've got a potential difference of 2.4 volts. So once it gets over to the other side, we're going to be down to, 997.6 volts. Remember the last time we lost 10 volts? This time we're only losing 2.4 volts. So if we work out how much we are losing, we could use P equals I squared R, nice and simple. P equals I squared R equals 0.24 squared times 10 equals 0.576 watts. If we decide to work out the other way, P equals IV, then we're going to get a current is going to be 0.24 multiplied by 2.4 equals 0.576 watts. Okay, so using P equals IV or using P equals I squared R, both of them work out to give us exactly the same answer as long as we use the correct voltage. The value here was power loss was 0.576 watts. Remember back on the other one, we had a power loss of 10 watts. So using a low voltage for power transmission means we're going to have a large power loss in the cables.